Hi there, and welcome to Raelene Math. In this video, we're going to look at the function f of x defined by the absolute value of 6x minus 12 over 4 minus 2x. And in particular, we're going to look at the value of this limit as x approaches 2 on this function. The first thing we want to do for every limit value, or every limit expression, is to work out the function value. What happens on this graph when x is equal to 2, to the y-coordinate? So we substitute the 2 in for x, and we get the absolute value of 12 minus 12 is 0, divided by 4 minus 4, which is 0. And this is indeterminate. When the y-coordinate on a graph is indeterminate, that suggests one of three types of discontinuity behaviors. The graph either has a hole in the graph, and therefore the limit will exist, or the graph has a jump discontinuity, which means that the left-hand height that y approaches and the right-hand height are different, and therefore the limit does not exist. Or we have an oscillation, which means that the y-coordinate is trying to take on an infinite number of heights as x approaches that value of 2, and therefore the limit does not exist. If we understand what this graph looks like, if we know what it looks like or have technology, we could evaluate the limit straight away. But if we don't, we need to use some other combination of numerical and algebraic techniques. This graph reminds me of a parent graph that I've seen before, and the parent graph is y equal to the absolute value of x over x. I know this graph to have a jump discontinuity because I've studied it before. But if you're not familiar with some of the parent graphs, you can use technology to see how come they behave the way they do. So here's the equation in Desmos, y equals absolute value of x over x, and almost all the time when we want to sketch a graph, we start off with a table of values. So I'm just going to make the y-coordinate equal to the absolute value of x1. I didn't type anything fancy there, just x1. And it's an empty list until I start to plug in some numbers. So let's substitute negative 3, negative 2, negative 1, 0, 1, 2, 3. And we see all of these different output y values. Specifically, when x is negative, the y-coordinates are all negative 1. When x is 0, y is undefined. This just means that y is not defined, or y fails either to be a real value, a single value, a single height on the graph, or a finite value. Maybe y is trying to shoot up to a height of positive infinity or negative infinity. Meanwhile, when x is positive, all the y-coordinates are positive 1. So you can take a look slowly and plug in and confirm this for the table of values. Now that we've got the table of values, we can look at the graph. And the graph passes through those points. Turn it on, and there we have it. So I'm just going to turn off the table of values, and we have our graph. We can trace along here, and we can see that as x approaches 1 from the right-hand side, as x approaches 0, we're heading towards the y-axis, that the y-coordinate approaches a height of 1, but when we get there, the y value is not defined to be anything. And that was consistent with our table of values. Similarly, as x approaches the y-axis, or the vertical line x equal to 0, from the left-hand side, y is still looking like it's on track to approach a height of negative 1. In fact, we're on a horizontal line. The height is constant. But when we actually get there, there is no y value defined. That's okay. The limit value doesn't care what happens when you're actually at that vertical line of x equal to 0, just what's happening as x approaches it. And so from the left-hand side, y approaches a different height than from the right-hand side. So when we have this y approaching two different finite heights, depending on coming from the left or the right, we say that the limit doesn't exist because we have a jump discontinuity. So we would say that the limit as x approaches 0 from the left on this graph is equal to negative 1, but it's not equal to the limit or the height that y approaches as x approaches 0 from the right-hand side of the y-axis, which is a positive 1 height. And therefore the overall limit as x approaches 0 on this graph, regardless of the direction that x comes from, does not exist. And the reason is that the y-coordinate is failing to approach a single height. We have real values and we have finite values for the heights of negative 1 and positive 1, but we don't have just one single height that y is approaching. So how can we use this parent graph to come up with this new f of x graph? Well, if we take the f of x function and put it into transformational form, the transformational form we find by doing a transformation of, or a factoring. So we can factor 6 in the numerator inside the absolute value, and we can factor a negative 2 out of the denominator. And we see a common factor, and the root of that common factor of x minus 2, the root of that is the value that x would equal to make the factor equal to 0. So if we solve x minus 2 equal to 0, we get the root of the common factor of x equal to 2. And it's not a coincidence that that's the x-coordinate we're plugging into this limit expression, because we want to know what happens for the discontinuity. So we should pause and remind ourselves to find the domain of all functions. We have a denominator that can't be equal to 0, which means that 4 minus 2x can't be equal to 0, which means that x can't be equal to 2. And therefore our domain of this blue function is all real values except equal to 2. This limit question is really just asking what's happening on that graph when x is equal to 2. What kind of discontinuity do we have? I think we have a jump, because I know the parent graph and I see some transformations occurring at x equal to 2 instead of x equal to 0. Right, so how do we take that function form and put it into transformational form? By the property of absolute values, I can separate the absolute value of 6 and the absolute value of x minus 2. And I have negative 2 over x minus 2 like this. So the absolute value of 6 is 6 divided by negative 2 gives me negative 3. And then I have the absolute value of x minus 2 over x minus 2 like this. If I were to take a substitution, let t equal to the stuff of x minus 2, then I could rewrite this equation as a function of t, and it would be negative 3 times the absolute value of t over t. What this would allow me to do would be to transform my red graph by doing a vertical scaling of 3 and a vertical reflection. That means instead of going to a height of negative 1 or 1, that my graph would go to a height of negative 3 or 3. But then I would have a vertical reflection in this graph, and my branches would swap directions like this. So according to this, as x approaches as t approaches 0 from the left-hand side, y would approach a height of positive 3, and vice versa coming from the opposite side of the y-axis. So I can take my limit as x approaches 2 on the graph of negative 3 times absolute value of x minus 2 over x minus 2, and I can transform it into a simpler limit where t approaches 0, because that is the new root of the common factor. In other words, when I let t equal to x minus 2, if I substitute 2 for x, then t is equal to 0. And so I'm going to represent that by t approaching 0, which is showing that I've had a translation. And then I can say my limit of the function negative 3 times the absolute value of t, getting tongue-tied here, all over t, is really a matter of looking at this graph. I look at that into two pieces then, because I have to see if the left-hand height and the right-hand height on the green graph are the same finite values or if they are different. From the left-hand side, as t approaches 0, y approaches a height of positive 3. But on the right-hand side, I'm checking to see if these are equal. As t approaches 0 from the right-hand side, so as t approaches the y-axis coming from the right, y approaches a height on this graph of negative 3. And since those values are not equal, we say that the overall limit does not exist. But because we have two different heights that are finite, we know that we have a jump discontinuity. And so we can just plug that final function into Desmos to see what happens in one step. We had y equals the absolute value of 6x minus 12, all divided by 4 minus 2x. And this grapher seems to have a little bit of a trouble graphing it. There's a vertical line here because it's really doing a table of values calculation. But we can see that on the graph of the x-axis at least, as x approaches 2 from the left, y is approaching a height of positive 3, and as x approaches the line x equal to 2 from the right, y is approaching a height of negative 3. So just to put that all into context, I didn't draw the blue function, I drew a simplified function. If I wanted to go back and sketch the function f of x, which was negative 3 times the absolute value of x minus 2 all over x minus 2, I would have taken the parent graph, which is y equals the absolute value of x over x, and I would have applied a horizontal translation of 2 spaces to the right, which means that the jump occurs at x equal to 2 instead of at x equal to 0, and I would have had a vertical reflection and a vertical scale of 3. So starting with my parent graph, which are at heights of 1 or negative 1, then I would get a new graph where the jump occurs at x equal to 2, because I've translated the jump at x equal to 0 2 spaces to the right, and I've scaled to heights of 3 or negative 3, and I've reflected. And so looking at a graph in terms of the variable x as the input, instead of my substituted new input variable t, I would be taking the limit as x approaches 2. But that's consistent with taking the limit as t approaches 0. If we do the substitution, we're kind of hiding the horizontal translation that we had. Okay, hopefully this makes sense. We can see overall that the limit value that we were studying does not exist because we have a jump discontinuity at the x-coordinate of 2 on the blue graph. Thanks for checking out Raelene Math.